Dear students, today's topic is the uni junction transistor, or popularly known as UJT. The topic code is ELEC-SPD-S2 Special Devices Section 2. This is the typical uni junction transistor. Symbolically, it is represented by this symbol, which has an emitter, base 1, base 2, and it is encircled around. The emitter symbol is little bit angled, little bit slanting angle, and pointed towards the plate. We have these base 1 and base 2, two bases. What we have in this case in uni junction transistor, as its the name indicates that it has a one single junction. So what we have suppose is a N type bar, N channel material, a long bar which is pretty have a greater length than the P type. What we do, we dope a P type material on the one side of the bar, which is closer to one of the bases. Let's say here is the base 2. So here P-N junction is formed. So this is the complete N channel. We could have P channel, then it will be the N type, the doped emitter. But in this case we have P type and N channel uni junction transistor. The equivalent circuit diagram, if you look at the two bases and the one emitter, it looks like this, that there is a RB2 resistance between the base 2 and this junction point, and the RB1 from this junction point to base 1. So this is simplified equivalent circuit diagram. The voltage is applied between the base 1 to base 2 is VBB, and we get the voltage drop across RB1 is eta times VBB. This is the diode, which is a P-N junction diode, D, and the other terminal, which is the positive side, is connected to the emitter. So this is the construction. Now let's move to the uni junction transistor. Is a 3-terminal semiconductor device which exhibits negative resistance and switching characteristics for use as a relaxation oscillator in phase control applications. So where we want to control the phase or other the vibrator or the relaxation oscillator, it is used over there as a switching characteristics mode. The uni junction transistor, or UJT for short, is another solid state 3-terminal device that can be used in gate pulse timing circuits and trigger generated applications. Short pulse triggered application, you want to operate a certain device or run the device, so that is the triggered application. To switch and control either thyristor is another device, special device, which we will be discussing another topic. Triax is also a device for AC power control type applications. Triac and thyristor and dioc, these are the other special devices. So for triggering these devices, this UJT transistor is used. Like diodes, uni junction transistors are constructed from separate P-type substances, semiconductor material, and N-type semiconductor materials, forming a single, hence its name uni junction, single P-N junction diode within the main conducting N-type channel of the device. Although the uni junction transistor has the name of a transistor, its switching characteristics are very different from those of the conventional bipolar BJT transistor or field effect transistors, as it can be used to amplify a signal, but instead is used as an on-off switch or on-off switching transistor. UJTs have unidirectional conductivity and negative impedance. characteristics acting more like a variable voltage divider during the breakdown. Like N channels FET, the UJT consists of single solid piece of N-type semiconductor material forming the main carrying channel with its two outer connections marked as base 2 and base 1. The third connection is confusingly marked as E or emitter, which is located along the channel. The emitter terminal is represented by an arrow pointing from the p-type emitter to n-type base. So this discussion I have already narrated, so you can read out. I think that will be easier. So again the same circuitry is given over here. So in this case we move on. Notice that in this case, notice the symbol of the unijunction transistor looks like very similar to the unijunction field effect transistor, except that it has a bent arrow or slanting arrow representing the E, emitter E input. So basis we have defined. Now we would like to here discuss about the resistances. Resistance RB1 is given between the emitter and RB2 and emitter E and the B1, while the RB2 is given between the E and the terminal B2. As the physical position of the PN junction is closer to the terminal B2 than B1, the resistance value RB2 will be less than the RB1. The total resistance of the silicon bar, its ohmic resistance, will be dependent upon the semiconductor actual doping level as well as the physical dimension of n-type silicon channel, what can be represented by RBB, total resistance we can say, which is the sum of these RB1 plus RB2. If measured with an ohm meter, the static resistance would typically measure somewhere between about 4 kilo ohm and 10 kilo ohms for most UJTs, such as these particular models 2N1671 and so on. These two series resistors produce a voltage divider network between the two base terminals of the unijunction transistor. Since the channel stretches from B2 to B1, when a voltage is applied across the device, the potential at any point along the channel will be proportional to its position between the terminals B2 and B1. The level of voltage gradient therefore depends upon the amount of the supply voltage. When used in the circuit, B1 is connected to the ground and the emitter serves as the input to the device. Suppose the voltage VBB is applied across the UJT between the B1 and B2, and B2 is biased positive relative to B1 with zero emitter input. The voltage developed across RB1, the low resistance of the resistive voltage divider, can be calculated. RB1 V voltage across the RB1 will be equal to RB1 divided by total voltage multiplied by the applied voltage VBB. For a unijunction transistor, the resistive ratio of RB1 to RBB shown above is called intrinsic standoff ratio. And is given in the Greek symbol eta. The typical standard values of the eta range from 0.5 to 0.8 for most common UJTs. If a small positive input voltage, which is less than the voltage developed across the RB1, eta VBB, is now applied to the emitter input terminal, the diode PN junction is reverse bias. That is, if the less voltage is there, so it will be reverse bias, thus offering a very high impedance, and the device does not conduct. Now the UJT is switched off and zero current flows. However, when the emitter input is increased and becomes greater than the V or V1, then eta VBB plus 0.1, that is VRB1, where the where is V eta V plus 0.7 volt, where 0.7 volt equals to the p-n junction voltage, is a barrier voltage drop of the diode, p-n junction diode becomes forward bias, and the unijunction transistor begins to conduct. Now the result is the emitter current eta IE now flows from the emitter into the base region. Now the effect of the additional current, emitter current flowing to the base reduces the resistive portion of the channel between the emitter junction and the B1 terminal. This reduction in the value of the RB1 resistance to a very low value means that the emitter junction becomes more forward bias, resulting in a larger current flow. The effect of this result is a negative resistance at the emitter terminal. Likewise, if the input applied voltage between the emitter and B1 terminal decreases, the value below the breakdown, the resistor value of the RB1 increases to the high value. The unijunction transistor can be thought of a voltage breakdown. So we can see that the resistance represented by RB1 is variable and is dependent on the value of emitter current IE. Then the forward biasing emitter junction with respect to B1 causes more current to flow, which reduces the resistance between the emitter E and the B1. In other words, the flow of the current into the UJT's emitter causes the resistive value of the RB1 decreases, and the voltage drop across it, RB1, must also decrease, allowing more current to flow, producing a negative resistance condition. Let's see the voltage plot, voltage versus current plot. In this case, here is this is UJT, the emitter current versus emitter voltage plot. When we can see that the voltage is less, we have the IEO, we call it the leakage current, which is in the reverse bias mode, or you can see it is a reverse bias mode. The current is very small and transistor is in the off state. But as the voltage increases and reaches the peak value, from here the diode is in the forward bias and start increasing. When it reaches to the peak value, this is the peak value, what happens that the N channel have a breakdown, a greater breakdown. Let me show you. So here what we have, when the voltage here is greater than this RB1, this the region between this the diode junction and the B1, the drastic the breakdown of this region takes place. So charge carry with negative coefficient of resistance, we say, and the very large amount of the current flows in this region, in that particular, after the peak value is reached. So that is we see that the large current amount here, the large current is flowing through, where the voltage is dropping. Then the voltage reached to the V valley, we call valley point. IV is the valley current, and the VB is the valley voltage, which is the drop due to the breakdown of that region of the N channel bar. So after that, when the voltage again the drops become less than the RB1, then what happens, then again the resistance increases, and so as the voltage also start increasing. So this is a very this is the region is called the negative resistance region of the UJT transistor. Okay, now unijunction transistor applications. Now that we know that the unijunction transistor works, that can be used for the most common application of unijunction transistor is as a triggering device of SCRs. Means you start a certain device. Triggering means a pulse, you generate a pulse and you want to start a certain device. SCR, silicon control rectifier, this is another special device which will be a separate lecture, you will be seeing that, and the triacs. But the other UJT application include the sawtooth wave generator. We want, if you remember in the oscillators, we said that the tank circuits and the other the RC phase shift oscillators or crystal oscillators, they are used to generate the sinusoidal waveform, and they are called sinusoidal oscillators. There are other types. Second type was a non-sinusoidal oscillator. This is the one of the application, uni-junction transistor, which is used to be used as a non-sinusoidal oscillator. So the sawtooth generator, simple oscillator, phase control and timing circuits, these are the applications. The simplest of all the UJT is the relaxation oscillator, producing non-sinusoidal waveforms. In basic and typical UJT relaxation oscillator circuit, the emitter terminal of the uni-junction transistor is connected to the junction of the series connected resistor and capacitor RC circuit, as shown below. Although the application is not in your course, but you can go through and see basic the construction and the mechanism, the working of the uni-junction transistor in your course. But this is the one typical uni-junction relaxation oscillator. You can read out, and you can very simple. You can correlate the things, and you can find out the positive pulse and negative pulse. These are the spikes, or the non-sinusoidal pulses which are generated by the UJT. So with this we reach to the end of the topic. Thank you.